Hello everyone, welcome to my class. Today I'm going to cover fundamental theorem for line integrals. It's the first big theorem in vector calculus. So let me start with some prerequisite definition. Simple curve. C is simple if it does not cross itself. It's example here. Closed curve. C is closed if its initial and terminal points are the same. Example here. Open region. D is open if it does not contain any of its boundary points. Example. Connected region. D is connected if we can connect any two points in D with a path that lies completely in D. So we can connect any 2 points inside the D with a path completely lies in D. Simply connected region. D is simply connected region if it is connected and it contains no holes. That means we can shrink the domain to a single point. Similarly, let me continue. The path independent. Let me scroll down. That's better. Path independent of vector field, which is denoted by capital F, is called the path independent if the line integrals of f over c equals to line integrals of f over d for any two paths c and d with the same initial and terminal points. So let's say the curve starts at P and at Q. One path is C path, another path is D path. We don't care what the path is, just we care the initial point and then the end points. If the line integrals over C equals to over D for any two path with the same initial and terminal points, we call the vector field is a path independent. Another definitions. A vector field F is called a conservative. Sorry, not liberal. Vector field is called conservative vector field if vector field equals to gradient of f for some scalar functions little f. Such a scalar function little f is called a potential functions for vector field. So the questions, let's ask to ourselves how to find a potential functions. Let me scroll down. Yeah. Suppose given vector field has component p, q, r is conservative. That is, vector field f equals to gradient f for some f. Then vector field is p, q, r. Gradient f is fx, fy, fz. Two vectors are equal if and only if the corresponding component are equal. So p equals to fx, q equals to f of y, plus r equals to f of z. Then how to extract our little f from these relations? So take integrations of p with respect to dx, take integration of q with respect to dy, take integration of r with respect to z, and in the x integrals, the yz stubs are constant. In y integral, xz stubs are constant, and in z integral, xy stubs are constant. And pick the little f satisfying all of these profiles. Great. Now let's do one quick example. Maybe that's better. Example 1 is given vector field a conservative. If it is, find a potential function little f such that vector field equals to gradient of f, or vector field is a gradient vector field. So suppose f is gradient of little f, then the partial derivative of little f with respect to x is the first component of vector field. Partial derivative of little f with respect to y is a second component of vector field. Partial derivative of f with respect to z is the second component of vector field. Then from these relations, f equals to integrate the first, this f of x with respect to dx, this f of y with respect to dy, and then the f of z with respect to z, then the integration of this y square z plus 2x z square with respect to dx is x y square z plus x square z square plus arbitrary constant, which is function of yz. And keep in mind, in x integrals, y and z terms are constant. So in the first one, here is a y square constant, z constant, so simply y square z times x. Here's 2 and z square constant, integration of x becomes x square over 2, 2 cancel, so x square z square. Similarly, integration of 2xyz with respect to dy is xy square z plus the constant. Integration of xy square plus 2x square z with respect to dz is xy square times z plus x square z square plus constant. So now pick of function little f satisfying this profile. So take this common terms, x y square z, x y square z, 1, and then pick the remaining terms. So here is x square z square, x square z square, another x square z square. We don't need to pick this one. We can take this constant equals to 0. Great. So we proved this given vector field is a conservative, and at the same time we found a potential functions corresponding to that vector field, which is little f, this one. Great. Now let's move on. Hence f is conservative. Now we have another a first important theorems, or the big theorems in vector calculus. For the gradient vector field, we have the following powerful theorem. We call FTLI, fundamental theorem for line integrals. So it says, if f is a gradient vector field, and c is a smooth curve given by the equations R of t, where t lies between a and b, with initial point R of a and ending point R of b, then the line integrals of f over c, that's a vector line integral, equals to find the potential functions and simply evaluate at the end point f of rb minus f of ra. So this computation is not that hard, so let me go over quickly. So that's just I'm just replacing vector field f by gradient f, and then here's gradient f is a function of rt, and dr is r prime t dt, and this is simply r prime t, by the way, this is dx over dt, dy over dt, and this is the gradient vectors. So this is simply fx dx over dt plus fy dy over dt outside dt, and this is simply the regular derivative of these compositions. And then let me scroll down. Yep. And from the fundamental theorem of calculus, from calculus 1, this is simply the derivative, and this entire derivative cancel. This is simply f composite r evaluate at t equals to a to b. So this gives us little f evaluate at rb, this is the ending point, and this is the minus f evaluated ra, which is the starting point, initial point and the ending point. That's it. Now let me do example 2. That's better. I think that's the questions I posed earlier in the previous sections. So evaluate the vector line integrals after dr over c, where f is given here and t is given here. Then we know by example 1 f is conservative. Let me scroll up. Yep, we proved this one here. This is a conservative, and at the same time we found the corresponding potential functions, which is xy square z plus x square z square. Let me use it here. Yeah. So using from example 1, we know the vector field, this given vector field is conservative, and its corresponding potential function is xy square g plus x square g square. Then using FTLI, fundamental theorem for line integrals, let's evaluate these line integrals. This equals to simply little f evaluate at the endpoint. Can I see the formula here? Yeah. F at endpoint minus f at this is the ending point minus the initial point. So this is the little f evaluate at the endpoint minus little f evaluate at the initial point. So our little f is here given. So endpoint is when t equals to 1. Initial point is when t equals to 0. So then this is the terminal point or ending point is put t equals to 1 here. 1, 2, 1. And f at initial point, so t equals to 0. 0, t0 is to 1, t0 is 0. Then the function is here. Let's evaluate. Put x equals to 1, y equals to 2 square, z equals to 1. So plus x equals to 1, z equals to 1. This is the f at ending point, means the terminal point, minus when x and z0, x0, 0, x0, so both terms are 0. So we just have 1 times 2 square times 1 plus 1 square times 1 square, which is 5. Great. Now let's move on. I can make it bigger here. Oh. So there are the equivalent conditions for conservative vector field. F is conservative if and only if F is a path independent. So that means the line integrals of F depend only on the endpoint of the curve. This is if and only if the line integrals over closed path. This tiny circle around here means this means the RC is closed. So for every closed path, the line integral is 0. And if f is conservative, then we can write f equals to gradient f for some potential functions little f, means f is a gradient vector field. This is if and only if f satisfies the following, which we call conservative vector field criterion, which is partial derivatives p with respect to y equals to partial derivative q with respect to x, partial derivative p with respect to z equals to partial derivative of r with respect to x, partial derivative q with respect to z equals to partial derivative r with respect to y, provided that the domain of f is open simply connected region. It's great. And drop out r and z for two-dimensional case. Now let's move on. Example 3. Let's do example 3. Is given vector field a conservative? Now I am going to use that one of the equivalence relations to answer this question. So here the domain of f is r squared, which is open and simply connected. So the next, and it's also defined on whole r. This vector field is defined on whole r squared, whole r squared. So next, let's find the partial derivative of, this is p, this is q, p with respect to y, which is 2y. Partial derivative of q with respect to x is simply 2y, so these two are equal, hence f is conservative. By the way, let me go up on this formula. If I'm in the 2D case, then the r0 and z0. So z0, this gone, r0, this gone, z0, this gone, r0, this gone. So I have only this one relation, which is py equals to qx. Okay, so that's what I showed here, py equals to qx, hence f is conservative. Example 4, compute, this is better, compute the line integrals over the closed curve, this is closed curve, of y square minus 2x dx plus 2xy dy, where c is as shown. This is this curve. So now, the idea is, we know this curve starts at point 32 and ends at point 32, so it's a closed curve, and we know this is a conservative y square minus 2x and 2xy. This vector field is conservative, so by one of the equivalent conditions, the line integrals over the closed curve is simply 0. Correct. So now let's move on. Example 5. So revisit example 3. So evaluate the line integrals of f over c, where f is given y square minus 2x, comma 2xy, and c is as shown. C is shown here. So now in example 3, we know our vector field is conservative, right? And then now this curve is not closed curve, so I cannot use this one of the equivalence conditions, but I'm going to use fundamental theorem for line integrals. So if our vector field is conservative, find the potential function. So here, let's find first the potential function. Here f is conservative, then we can write f equals to, means vector field equals to gradient of f for some scalar function f. So then the partial derivative f with respect to x equals to the first component of vector field. Partial derivative of little f with respect to y equals to the second component of vector field, which is p and q. So q, extract the, let me scroll down, extract the little f from these two equations. So integrate partial derivative x with respect to dx, and integrate partial derivative of y with respect to dy. So then its integration with respect to x becomes y square constant, so y square times x minus x square plus function of y, which is a constant. Now its partial derivative with respect to y is simply xy square plus the constant function of x. This is constant for y integral, this is constant for x integral. And pick f of xy equals to this y square x minus x square. And we don't take those constants, we assume those constants are 0. Just that means this is true for any arbitrary constant, and we pick that constant is 0 without loss of generality. Okay, so let's use fundamental theorem of line integrals to evaluate these line integrals. Then the line integrals of vector field f over c equals to gradient f, line integral of gradient f over c equals to, all we need the potential function evaluated at the end point. So then this is the potential function we found here, going from 1, 0 to 2, 2. 1, 0, let me go back here. So 1, 0 is our initial point, 2, 2 is our ending point, or the terminal point for this curve. 1, 0 and 2, 2. So this equals to the function xy square minus x square, evaluate at 1, 0 to 2, 2. Put upper limit, so x equals to 2, y equals to 2 square, so 2 square 4 times 2 is 8, minus 2 square is 4, this is coming from the upper limit, and then minus from formula, put x1, y0, so y0 gives me this 0, then this one gives me minus 1, x equals to 1, so that minus and formula minus is plus, so then 8 minus 4 plus 1 is 5. So we use fundamental theorem of line integrals to evaluate these line integrals. Great. So we finish these sections. So in the heads up, in next section or next lecture, we'll cover Green's theorem. Thank you.